Greetings, differential equation scholars, and welcome to the third installment in our video series on section 7.1 of your text. In our first two videos on section 7.1, we looked at the definition of the Laplace transform, and we applied that definition to find the Laplace transforms for, in one case, a constant function, and then we used it to find the Laplace transform for an exponential function. Now that we have the definition of the Laplace transform under our belt a bit, we're going to take a look in this video at a very important property of the Laplace transform. And that is that the Laplace transform is what we refer to as a linear transformation. Now, what do we mean by that? Well, you remember from Calculus 1 that integrals have some very useful properties. One of those properties is what we call the constant multiple property, so that the antiderivative of k times a function f is k times the antiderivative of f. We call that the constant multiple property. Then also we have an addition property for integrals, which says that if you have the antiderivative of the sum of two functions, f and g, that antiderivative of that sum of functions is the sum of the individual antiderivatives of f and g. So when you combine those two properties together, the constant multiple property and the addition property, we say that integration is a linear transformation. Because it has those two properties. Now, because integration works in that linear sort of fashion, and because the Laplace transform is defined as an integral, that means that the Laplace transform also has those same linear transformation properties that the integral itself had. And so what does that mean? Those two properties, the constant multiple property and the addition property, taken together tell us the following. Suppose we have a pair of real constants, alpha and beta. And suppose we have two functions, f and g, whose Laplace transforms we know. And we're interested in finding out the Laplace transform of this linear combination of alpha times f plus beta times g. Well, because of the linearity of the integral, that means necessarily that the Laplace transform of alpha times f plus beta times g will be alpha times the Laplace transform of f plus beta times the Laplace transform of g. That follows directly from the fact that integration, antidifferentiation, has those properties. Now that's wonderful, because what that means is once we start discovering what the Laplace transforms of certain functions are, we can find the Laplace transforms of other functions by using this linearity property. So let's look at a first pair of examples of that. You may recall that in a previous video, we showed that the Laplace transform of a constant was just that constant divided by s. So the Laplace transform of 5, for example, is 5 over s. We also showed that the Laplace transform of an exponential function, e to the at, is 1 over s minus a. So, for example, the Laplace transform of e to the 2t would be 1 over s minus 2. So we know these two transforms, the Laplace transform of 5 and the Laplace transform of e to the 2t. Now, suppose somebody comes to me and they say, well, Mr. General, what's the Laplace transform of 5 plus 3 times e to the 2t? Well, I know that this is just a combination of those other functions. This is 5 plus 3 times the other function. So because of linearity, the Laplace transform of 5 plus 3 times e to the 2t is going to be the Laplace transform of 5 over s, plus 3, that constant, times the Laplace transform of e to the 2t. And that means that I know what the Laplace transform of this sum is. It's 5 over s plus 3 over s minus 2. That will be the Laplace transform of that sum of functions. As another example, suppose we have a difference of two exponentials, and we want to know what the Laplace transform is for this difference of exponentials. We want to know what the Laplace transform of 3e to the t minus 2e to the minus t is. Well, we can find that using the linearity property. We know on one hand that the Laplace transform of e to the t will be 1 over s minus 1. And we know that the Laplace transform for e to the minus t will be 1 over s plus 1. So therefore, it follows from that that the Laplace transform of this difference will be 3 over s minus 1 minus 2 over s plus 1. That will have to be the result because of linearity. In section 7.1, a very important result is shown that has to do with the Laplace transform for powers of t. It's shown in that section in your reading that if you want to know the Laplace transform of the nth power of t, that is actually a fraction that contains the n plus first power of s in the denominator and the factorial of the power n in the numerator. So for example, suppose we had t to the first power here, and we wanted to know what's the Laplace transform of t to the first power. Well, in this particular case, since that's a first power, we'd end up with a second power of s in the denominator and 1 factorial in the numerator. So the Laplace transform of t is 1 over s squared. If we want to know what the Laplace transform for t squared is, well, since we're starting with the second power of t here, we're going to end up with a third power of t in the denominator and 2 factorial in the numerator. So the Laplace transform of t squared is 2 over s cubed. If we want to know what's the Laplace transform of t to the third power, well, I'm going to have a fourth power of s down in the denominator and 3 factorial, which is 1 times 2 times 3, or 6 in the numerator. So the Laplace transform of t cubed is 6 over s to the fourth. This is a very useful rule by which we can find the Laplace transform for any power that we want. This is an important rule to memorize and to commit to memory, this result about the Laplace transform for powers of t. Now, if we can use that, if we use that rule, we can put it together with the linearity property to find the Laplace transform for really any polynomial. Suppose we wanted to know what is the Laplace transform of minus 3t plus 7. Well, that's the same thing as minus 3 times t plus 7. And since we know what the Laplace transform of t is, it's 1 over s squared. And since we know what the Laplace transform for the constant 1 is, it's 1 over s. That means by linearity that the Laplace transform of minus 3t plus 7 is minus 3 times the Laplace transform for t plus 7 times the Laplace transform of 1. So we have minus 3 over s squared plus 7 over s. And that will be the Laplace transform of this linear function. As a final example for this video, suppose somebody asks us, what is the Laplace transform of the square of 2t squared minus 1? Well, that's an algebraic expression. And if we expand out 2t squared minus 1 squared, we know that algebraically that expands out to 4t to the fourth minus 4t squared plus 1. And that's just a polynomial. We'll break it up into pieces. The Laplace transform of 4t to the fourth minus 4t squared plus 1 will be 4 times the Laplace transform of t to the fourth minus 4 times the Laplace transform of t squared plus the Laplace transform of 1. Now the Laplace transform of t to the fourth will be 4 factorial over s to the fifth. 4 factorial is 1 times 2 times 3 times 4, and that's 24. So 4 times the Laplace transform of t to the fourth is 4 times 24 over s to the fifth. And that comes out to be 96 over s to the fifth. Since the Laplace transform for t squared is 2 over s cubed, then our middle term here gives us, when all is said and done, a contribution of minus 8 over s cubed. And of course, the Laplace transform of 1 is 1 over s. So what is the Laplace transform of the square of 2t squared minus 1? After using algebra and using the linearity property of the Laplace transform, we find that it's 96 over s to the fifth minus 8 over s cubed plus 1 over s. Those are some examples of finding Laplace transforms using core results that we've established and using the linearity property of the Laplace transformation. This linearity property is immensely useful, and we'll be continuing to use it heavily as we move forward. Stay tuned. Next in our series of videos, our fourth and final video from section 7.1 will be a video showing the Laplace transform of a piecewise defined function. So stay tuned to this YouTube channel for more details soon.